Okay, hi everyone. So this is CHEN 430 Process Design 1. This is lecture 4, week 4. We're talking about sequencing separation trains. So we're going to start introducing the idea on how to arrange your separation steps if you want to separate mixtures having more than two components and what's the logic in doing so. And in this lecture, we'll just talk about the different technologies, give you a reminder. It's sort of complementary to what you'll be covering in mass transfer this semester. So to try to get a bigger picture of what's going on. Okay, so September 14th, this is when this lecture will be released. Process heuristics continued. So this was the original plan, but we did all of the process heuristics last week, and then in this video we'll talk about introduction to sequencing, and then Aspen Plus tutorial number 3 will be posted as a separate video. Aspen Plus tutorial number 2 is due today. However, you have 2 more weeks. Homework number 1 is due today. It's a group submission. So please, only one person from each group should submit it. Your project topic selections are also due today. And homework number 2 will be assigned today as well. And a solution video will be posted before the deadline. One note about Aspen Plus. So I got this question a few times. If you're not sure how to save it from the, online access or, virtual machine onto your computer, just email it to yourself, right? That's the easiest way to get around it. Sometimes you can recognize your hard drive from your laptop and through the virtual machine, but if you're unable to do so, just email it to yourself, save yourself this headache. Okay, so let's get started. So we'll be talking about separation, and almost all chemical processes require the separation of some chemical species. And the objective of separation, you either want to purify a reactor feed, right? You want to recover some unreacted species to recycle back to a reactor, or separate and purify the products from a reactor, right? So again, as we said before, your separation step could be either before a reactor or after a reactor. Of course, there are processes which are only separations. For example, crude oil distillation. You get the crude oil, you have one large distillation column at 1 atmosphere. You have a second distillation column at vacuum, basically. And then you get all the different cuts. So you either want to purify a reactor feed or some raw material. You had a reaction and you want valuable reactant you want to recycle back. So you have a separation step. You have a reactor and you have a product with a bunch of side products. You want to separate your product, which makes you the most money, right? Okay. And usually the largest operating cost is associated with separation. And this point, the better way to phrase this point, or the more generalized way to phrase this point, is your largest investment and operating costs are usually associated with pieces of equipment that require a phase change, So if you're turning a liquid to a vapor, turning a vapor to a liquid, you're pumping large amounts of liquid, pumping large amounts of vapor. The most energy intensive units usually have the highest cost. And most of the time, your most energy intensive units are your separation units. And of course, for a binary mixture, so if I only have two components, I could only have one separation step, which accomplishes it in one task. However, in industry, or when you're designing a plant or in your design projects, most of the time you have more than one component. You could have 2 components, you could have 50 components. And this will involve a more complex separation system, and will involve a bunch of steps, and is usually referred to as a separation tree, right? So the objective of this lecture is you need to be familiar with the more widely used industrial separation methods and, their basis of separation, their logic, their driving, the driving force for the separation, all of this stuff. And you need to understand the concept of the separation factor, and eventually, later on, maybe by next semester, be able to make reasonable decisions based on this separation factor. And this separation factor, you're going to cover it in mass transfer with Dr. Ilyas. So just know how to calculate it and be aware of what it does or what it represents thermodynamically. Okay, so let's get started by just giving you a quick primer on distillation. So distillation, most commonly used separation process in the chemical industry. This is what a distillation column looks like. It's just a big tower basically, and you see has a bunch of usually a bunch of stairs around it. It's relatively cheap compared to other separation processes, and considering the large volumes it can deal with, it's highly reliable. So it's the type of thing which has been done forever, for a very long time. There's a lot of know-how in the process industry, even in fundamental science, understanding of the fundamental science. And when designing a plant, your distillation costs are usually the highest. Capital cost could be up to 80% for some processes. And the nomenclature for your distillation column. So this is the typical nomenclature, a typical way it's presented. So you have your feed right here. You have a bunch of trays. Your column has trays or has stages, whatever it is. From the bottom of your column, you get your bottoms, which is typically a liquid product. And then you have your reboiler. So the purpose of a reboiler is to just try and heat up some of the remaining light ends in your bottoms and reintroduce them to the column so that you enhance your separation efficiency. And the reboiler usually takes in some heat, QR. Then from the top of the column, you have your distillate, which is basically your main vapor product or your main light end. And from the distillate, you have a reflux drum. So the idea of a reflux drum is to try and condense some of the heavier ends from the distillate and recycle them back to the column. This could flow this way or could flow this way. So the arrows here show it this way. And then you have some vapor product, and condenser is so you usually basically have a heat exchanger called a condenser before introducing your fluid to your reflux drum. And sometimes on your process diagrams, this heat exchanger could be represented here, but the idea is the same. And usually have parameters controlling this. So you can have a reboiler ratio, talked about in Aspen, reflux ratio, whatever it is. And this is basically this ratio of the split right here, and the ratio of the split, right here, right? And usually sometimes this bottoms here, the split is represented after it leaves your cup, okay? And your feed, so basically your feed is separated into distillate, which is your light end, high volatility, lower boiling point, etc. And your bottoms, which is your heavy end, your heavier component, low volatility or lower volatility, whatever it is. Vapor is generated in the reboiler and passes up through many trays to the overhead condenser. So again, as we said, the whole purpose of this reboiler to try and get some of the remaining light ends from the liquid product and just introducing it back to the distillation column. These light ends will move up their way, and if the light ends have heavy ends dissolved in them, these heavy ends will come back, and then the light ends will continue upwards, and the liquid reflux flows down. Same idea here at the top. So I try to condense some of the heavy ends and reintroduce them back to the column so that I enhance my separation. Okay, so now I'm going to introduce two definitions. The first one is recovery. So definition of recovery, it's the fraction of a component's flow rate in the feed that's recovered in either the distillate or the bottom, right? So if I have the feed, it has component A and component B, and 50 or 90% of A leaves the distillate. So I say the recovery of A in the distillate is 90%. And if 75% of B is recovered at the bottoms, I say the recovery of B is 75%. And purity is the mole fraction of a component in either the distillate or the bottoms. So I could recover 90% of A in the distillate. However, this distillate feed is only 50% pure, right? So even though I recovered most of my A, but this recovery is not very efficient, right? I have a lot of junk with coming out with A as well. Another thing to know is that distillation column only has 2 degrees of freedom, split fraction, energy balance, and so only 2 things can be specified. And this is something to keep in mind as we progress, especially through the Aspen tutorials. when you start thinking about how Aspen deals with these distillation columns. And of course, specifications must be feasible. And you'll feel this a lot more with when dealing with Aspen, where, as we start dealing more with these distillation column separation equipments, find out that they're harder to converge, always give you a bunch of errors. You have to be very sensitive with the thermodynamics. Okay. Another concept you're going to see a lot when talking about distillation or dealing with distillation is the idea of a theoretical stage. And theoretical stages is basically sort of a mathematical artifact or a mathematical representation to what actually goes on. And it's also a good basis to estimate how the dimensions of your column, right? So theoretical stages, they're useful to understand distillation. The idea of a theoretical stage is I'm going to divide my distillation column into small pieces, and I'm just going to do the math or the mass balance around every piece separately. And this helps me identify the efficiency of each stage of this column. So maybe you have a column and you split it into 30 small pieces and do the math over every piece. I find out that most of the separation happens in the lower 12 stages, right? Or, most of the separation happens in the upper 12 stages. Whatever it is, it gives you a better idea about what might actually happen inside a real column or your finalized design for this column. And of course, real trays do not usually achieve theoretical tray performance. You have a tray efficiency, you have correction factors, you have other things to try and make these two numbers or these two performances match. So what really happens in a tray, sorry? So if you think about it, your tray is a multi-phase system, right? You have gas, you have liquid, etc. So the easiest way to think about it, or this is a good representation of it, where your liquid comes down a downcomer from a tray above and is distributed across the active area of a tray, right? So this line right here is your tray, and your tray is basically a perforated plate with some nozzles or some sort of perforations with a certain design. And your liquid comes down from the top, it spreads across this tray and eventually leaves down to the second tray and then spreads over the plate or the tray below, etc. However, at the same time, you have gas coming up, you have your vapor coming up, and this vapor, it will come into contact with the liquid and you'll start seeing bubbling, you'll start seeing frothing, and then at the very top, you'll see a spray phase or a spray continuum, right? So usually between trays, you have a stable liquid film here, and then you have some bubbling, then you have some frothing or foaming, and then after the foaming, you have some spray. And at this point, or near the bottom of the tray above it, this part is mostly vapor, and as it leaves to the tray before it. And of course, the liquid frothing and the liquid film or liquid, continuum drops to the stage below, and then here you have the same phenomena where I have gas coming up, you get a stable liquid phase, and then I have some bubbling, I have frothing, and then spraying, spraying very small particles of liquid, and then near the very top, it will be mostly vapor, okay? So liquid comes down a downcomer from the tray above, distributed across the active area of the tray. Vapor bubbles come up through the holes, creating frothing, and then froth or liquid overflows to the next downcomer, and etc. And it goes along your column height. Some columns use packing instead, and it's the same idea. So instead of using trays, some columns have some packing. We're gonna see it in the next slide. It's like small pieces, usually made of plastic, made of ceramic, to enhance the area available for mass and heat transfer. Okay. So when designing binary distillation or when trying to identify your operating regions for binary distillation, you usually need to design a McCabe-Thiele diagram, right? So if you have taken mass transfer before, you should know what a McCabe-Thiele diagram is, should be able to easily recall it or easily recall the procedure from a book or whatever. But this sort of diagram, once you cover it in mass transfer, it is the starting point to design your distillation column. And usually I have two components. I draw two lines here. I have my equilibrium line, and then I start staging off. And if I count these number of stages, this gives me an indication to the number of theoretical trays that this distillation column will have. And then I take this number of theoretical trays divided by the tray efficiency. I get the finalized number of actual trays in my distillation column. And of course, there are different cases. You know, if you have all types of mixtures, they behave differently. Sometimes you have azeotropes. Sometimes you have very weird curves. However, you have to be careful when dealing with them when designing your McCabe-Thiele. We're going to talk about this a lot in mass transfer. Okay. So just once you start covering McCabe-Thiele, open your ears, right? Okay. Azeotropes. And azeotrope, again, is a mixture in which my volatility order changes, right? Where I have my TXY or my YX diagram, I have this cross. So at this point, you know, this species is more volatile, and then, but after a certain concentration or a certain mixture composition, this species starts becoming more volatile. And you can have minimum or maximum. So instead of having it in this direction, it could be the opposite direction. And it's common for mixtures with high polarity or hydrogen bonding, that type of thing. Okay, so water oxygenates, just be careful with them. They always make azeotropes. Okay, so multi-component distillation, and this is the more common type of distillation in industry, as opposed to binary distillation where we only have two components. So in industrial problems, there are almost never just two components. Usually start for a mixture with many components, and you need to be able to trace these components all the way to the end, right? And multi-component distillation cannot be solved graphically. So even though we've talked about this McCabe-Thiele, which we're going to use to design distillation columns, however, this is only for binary distillation, right? Two species. When I have a bunch of them, you can't really do it graphically, right? You can use the graphical methods or these shortcut methods to give you an initial estimate, but the calculations become very complex because, you know, thermodynamics now start becoming complex. You have more than one species. You know, if you recall from mixture calculations in thermodynamics, calculations become, you know, more difficult, need more computational time, etc. And you can always use MATLAB or use some sort of computational tool, computer, whatever, to make it quick for you, or to create a standardized calculator for these types of things. However, by hand, it becomes very complex. And again, multi-component distillation are always designed using commercial process simulators. And you know, chapter 4 is from the book by Towler and Sinnott. So it's a good book. I don't use it a lot, but if you're interested, you can find it and have a look at chapter 4 and our lectures on simulation as well. We're going to talk extensively about distillation of multi-component mixtures. Okay, another idea in distillation is called stage efficiency. And we said that your theoretical stages, or calculating the number of theoretical trays, is a good initial estimate. However, it does not always reflect to your actual distillation column design. So in order to bridge this gap, we always have an efficiency, where the efficiency refers to a number of theoretical stages divided by the number of actual trays for the same separation. And so, for example, if we calculate 12 theoretical stages, and you look up through the manuals, or you look up through the white papers from previous industrial experience, and you find out that the stage efficiency for the process you're designing is somewhere around 70%. So you can divide your theoretical stages by the efficiency to get the number of actual stages. Okay, so this will be the end of the concepts we're talking about for distillation. Now we're going to move on to another very common type of separation process in industry, absorption and stripping, okay? And so the idea of absorption is I'm using a solvent or a mass transfer agent to selectively absorb or dissolve a component from the vapor phase into a solvent, right? And you regenerate the solvent by stripping using either steam, air, nitrogen, or a solvent. And there are two types of solvents. You have physical solvents, and physical solvents depend on the solubility, and solubility refers to the rate at which species A dissolves in species B. And the second type of solvent is a chemical solvent in which I have a reaction, right? So species A reacts with your solvent to form a third type of species. And these are very common examples. So for physical solvents, you have methanol, you have PEG-DMA, Selexol. For chemical solvents, you have MEA, DEA, MDEA, etc. Okay, so let's have a closer look at this idea of absorption and stripping. Okay. So let's say, so this is an amine absorber. So amine is being used as a solvent, right? And as you see at the bottom here, it's for removal of H2S and CO2 from gases and using solvents such as MDEA. Okay. So here I have a feed gas. So let's say my gas is let's say it's hydrogen and CO2, okay? Or methane and CO2, or methane and H2S. So you want methane, you want your methane because it's your gas of interest. You want to use it maybe to run a power plant, or you want to use it, you know, to run a boiler or something. But you want to get rid of this H2S and CO2 from the methane, right? Because H2S is highly corrosive, CO2, lots of emissions, etc. All of this stuff. So the feed gas comes in to the bottom of this absorption column. The feed gas will move up the column, and then from the top of the column, you have a liquid coming in. This liquid is called the solvent. And as the gas is moving upwards, the solvent is moving downwards. They get into contact with each other. They dance with each other, etc. And what happens in the solvent is that, so this solvent will have a high affinity for H2S, for example. So the solvent will basically eat up all the H2S from this gas mixture, and the clean methane will leave from the top, right? So from the top here, I'll only have methane, CH4, without any of the H2S. And then the H2S and the solvent will both leave from the bottom of the column, okay? So here it's called a rich solvent. So this rich solvent will go through, usually a heat, a step to heat it up or to cool it down. Whatever, usually have heat integration, doesn't matter. So it just passes through some pressure temperature manipulators and it enters to the top of this column, and this is called the stripping column, right? So here at the entry of your stripping column, you have your solvent and you have your H2S or whatever gas you're trying to remove. It enters from the top of the stripping column, it moves down, and as it's moving down, the two species separate, right? So the H2S will separate, leave from the top, and your lean solvent, which is a solvent without the H2S, will drop from the bottom. Okay, so the H2S now leaves from the top, it gets cooled down, and I get my acid gas, which is the H2S. And then from the bottom, I get the clean solvent without the H2S, and it's pumped back to my absorption column right here, right? So this is a typical absorption stripping cycle. Again, the whole idea of this absorption column is that I'm using a solvent which has a high affinity to one of the species, and it's going to eat up this species from the feed stream, and then I'm going to get the treated feed stream or the treated gas from the top of the absorption column. And then from the bottom of the absorption column, I get the rich solvent, which is a solvent, plus the species which it just ate up. This enters to a stripper, and the stripper basically strips this liquid solvent from this gas just absorbed. And again, this stripper could be, most of the time it's a temperature type of stripper. Sometimes it's a pressure stripper where I change the pressure suddenly or change the temperature suddenly, and you know, the gas bubbles out of the liquid, and you get the acid gas, or your the gas which was just absorbed as a separate component, pure component, and then I get my clean solvent, usually called the lean solvent, get it down from the bottom here. I pump it back up and recycle it back to my absorption cup. So again, as you can see, your solvent is always in a closed loop, whereas my feed gas enters here, clean gas leaves, and the acid gas leaves on top. Okay, so this idea is very important, or this type of process is applied a lot industrially. And it's very common to treat things like CO2 and H2S, where, you know, I can't really use distillation for this. And it's used a lot for gases. So, you know, distillation being used for liquids makes more sense. Absorption stripping, more for gases, makes more sense to use it. Okay. And when dealing with absorption and stripping, you're always governed by Henry's law, right? Henry's law is basically a straight line between the y and the x, and you're going to cover Henry's law in mass transfer. And then increasing temperature increases the slope of this equilibrium line, makes stripping easier. For chemisorption, you know, for very specific cases, this line might be, you know, curved or whatever. And these are special cases. Read them off the slides, but don't worry about them a lot. The most important thing I need you to know is the first point. So if I increase the temperature, stripping becomes easier, right? You need to be able to know this. All right. So again, in industrial practice, absorbers and strippers are designed using commercial simulation programs. Most of the time it's Aspen Plus. Sometimes there are other unique packages which does this design, because the calculation becomes a bit complex as I have a bunch of stages as my solvent becomes saturated. You know, if the gas is hot and the solvent is cold, I also have a heat transfer type of effect. So now equations are starting to pile up, right? So it becomes easier to use a simulation package. And you can always do a backhand quick calculation, you know, to check your L over G, all of this stuff. And optimizing this requires a trading off between your solvent circulation versus the number of trays, right? So usually have a trade-off in designing absorption and strippers, where if I maximize my number of my solvent flow rate, I'll need to have more trays to treat it, or if I decrease my solvent flow rate, I'll need less trays, or whatever it is. So most of the research, for example, in this area, focuses on the nature of the solvent, the molecular structure of the solvent, how quickly can it eat up this gas, in addition to the design, internal design. How do I maximize the contact between the gas and the liquid? Okay, to try and offset this trade-off. Okay, and again, this is very similar to what we talked about before, the tray dimensions. So again, when dealing with trays, these are very common type of language or nomenclature which you'll come across. You have your tray spacing, which is the distance between the trays. Your downcomer backup, which is the distance of this downcomer. Your downcomer clearance, which is the distance allowed for the liquid to enter into the next tray. The height of the next downcomer, and then you have your weir height, which refers to the active area of your tray, right? So just a few things. So if you ever hear weir height, weir length, whatever it is, downcomer, this is what it refers to. And when it comes to these trays, there are a bunch of different types that we're just going to talk about, maybe 4 or 5 of them. First type is called a sieve tray, and this tray just has a bunch of holes in it. So it's just a perforated plate tray with holes in it. Liquid is retained by vapor upflow. So, you know, the vapor is pushing through these small holes, and it's basically keeping the liquid from just, you know, weeping through the tray. So this is what it's called. So if your vapor velocity is not high enough, the liquid will start coming down, droplets, and it's called weeping. You know, the tray is weeping, means it's not performing well. This is the cheapest design. It's resilient to solids, corrosion, All this stuff has the lowest pressure drop. However, the performance is poor due to weeping again. So this type of tray is prone to having liquid just dropping through and not having a very high efficiency. So ideally, you don't want to have any liquid coming through these holes. You want the liquid to pass over the tray and come down from the downcomer. Second type of tray is called a valve tray. So if you look at it here, I have valves, and with this design, and the valves basically push the gas to leave from the sides, or instead of just bubbling straight up, they bubble from the sides. And moving valves close when the vapor flow is low. So if the vapor flow is too low, this valve will just shut down. So to avoid weeping, so it solves the problem of the sieve tray of having the weeping by having this sort of valve. So the vapor flow is high enough, the valve opens, the gas leaves. If the vapor flow is not high enough, the valve will just close and you won't have any weeping, right? If the valves fall off, then it turns into a sieve tray. So I mean, industrially, you don't want this to happen, but if you just introduce a very high vapor flow rate, these valves might just come off. But in industrial applications, there are many fancy designs to prevent this. There are a lot of proprietary designs, as we said. So every company comes up with a unique design. Changes the shape at the top, changes the shape of the cap of the valve, whatever it is, gets patented for this company. So you have UOP has this technology, Chevron has this technology, all of this stuff has a better performance than your sieve tray, right? But it costs more than your sieve tray about 1.2 times. So again, there's always like a trade-off with these things, and these are very extreme details. You usually wouldn't deal with this trade-off unless you become like a installation technologist, or it becomes your career. Okay, third type of tray is the fixed valve. So again, it's similar to the previous one, except this one does not move. So the previous one, the gas has to push it, open it. This one is just the valve is just stamped onto the tray, so it's always open. However, because of this design, the liquid head pressure is not fully applied on the surface area of the valve, so it prevents the sweeping somewhat. It's less prone to corrosion. One side is always open, so the orientation of the tray is important. So you don't want these looking the direction of the liquid, right? Otherwise, the liquid's just going to drain through them. And costs about 1.1 times of the sieve tray. Let's move on. Last one is bubble cap. And again, this bubble cap is very similar to the valve trays and ensures that the liquid level is maintained in each tray. Has a better turn down performance. Cost can be double that of the sieve tray. Pressure drop is much higher because in a bubble cap, you can, if you look closer at the design here, let's call it your sieve has a cap on it, right? So the gas moves up, it hits the top of this cap, and then it flows downwards, and then it leaves upwards, right? So moves up, hits the top of this cap, moves downwards, and moves upwards. And this fully prevents any weeping, right? Hydrodynamically, it's very hard to have any weeping. However, it results in a lot of, pressure drop is high because the gas now entering, it will lose a lot of energy, hitting the top, lose a lot of momentum, coming down, loses a lot of momentum, so you end up with a large pressure drop. And this has been very popular a long time ago. Now it's not used a lot. Now there's a lot of fancy designs with fixed valves and normal valves for distillation column. Okay, moving on. Packed columns. So sometimes instead of trays, you have I put a bunch of packing inside this column, and the idea or the reason of having a packing is to maximize the surface area, right? So when it comes to trays, or when it comes to having these trays, my surface area is limited to how many basically holes I have in this tray, the distance between the trays, the property of this gas, will it form enough bubbles, all of this stuff, right? This determines the area available for mass transfer. However, with a packed column, it maximizes this area significantly. There's minimum resistance to gas flow. So in this case, the gas does not have to push through a liquid continuum to make a bubble. There's just always intermingling. It enhances gas flow across the cross section of your column. So in a trade distillation column, because the gas has to bubble through the liquid phase, sometimes a tendency for the gas to converge towards the center. However, with packed columns, you don't have this problem. It enhances mixing, it enhances liquid distribution, etc. So this is sort of an advanced design for a distillation column. However, it's very difficult, much more difficult to manage, much more difficult to troubleshoot. Pressure drops can be high. So it's used in some applications, but commercially, you might find a lot of trade columns because they're just simpler to deal with. There are two types of packing: random packing, which is dumped, and then structured packing, which is metal sheets with holes and patterns punched into them. We'll have a look in a second. So random packing, these are common designs for random packing. You have ceramic ring, you have metal, cylinder. You have a ceramic, this is called a pal ring. It's called a rashing ring, burl saddle. This is a burl saddle. This is your interlock saddle, high pack, super interlocks, whatever. And this is what they look like. They're usually very small, maybe 1 inch, half an inch, different designs. You can really get into these details. And I just fill the column with these little guys, right? So the column is just filled with with this random packing, sorry. And the gas comes from bottom, liquid comes from the top. Because these packings have a lot of surface area here, the liquid spreads over the small packing, the gas moving through. There's a huge interface for gas-liquid contact, and the separation performance is usually better. Okay, so this is the idea of these types of columns. And as you can see, these designs, okay, sorry, going back. So random packing, as you can see, the designs evolve to maximize the surface area on the packing surface, so that I would have a larger area for gas-liquid contact. Okay, moving on to structured packing. And as we said before, structured packing are just metal sheets. So if you think about it, they are just metal sheets corrugated and put in parallel with each other. And these metal sheets have holes in them. And they're usually folded or stamped perforated sheets assembled into a block with high voidage. And they give better efficiency than random packings because, it minimizes some of the operational difficulty of dealing with random packings, but it's much more expensive than random packing. All right, and typical packing efficiencies, you can find all of this information if you have Perry's Handbook of Chemical Engineering, even online, whatever it is. And every packing efficiency has its own, every packing type has its own efficiency, has its own porosity, all this stuff. You can find all of these details in manual. Perry's Chemical Engineering book has a very good chapter on this stuff. Has all these details. If you're interested, just go look there. Okay, so if we compare trade versus packed columns, trade columns allow you to deal with a wider range of liquid and vapor flow rates. It's easier to design and predict stage efficiencies, easier to withdraw side streams, use side columns, or provide intermediate heating and cooling. Again, easier to clean. You don't have to worry about liquid distribution. So it's better for larger diameters. And it's usually cheaper. Packed columns, the properties are, they're not good for low liquid rates, You always need to have liquid zipping through them so that, all this packing will be covered. It's cheaper for corrosive systems. Reduced liquid holdup, so I have less liquid in this column at all times because liquid is not being retained, unlike the trays. So liquid just flows downwards. So it's safer for the system when our inventory must be minimized. So in cases where the liquid is volatile or there's a safety issue. It's good for high liquid throughputs, similar to the first point. Lower pressure drops, so it's better for vacuum columns, again. Cheaper for smaller columns where trays are difficult to install. However, as the column diameter increases, they become more expensive, and they're better at handling foaming systems, right? So sometimes in installation columns, you get foam. You can add some additives to deal with this foam, but these columns deal, if you want to forget about these additives and just have a battery system deal with compact columns usually do the job. Okay. Packed column design, simulation programs, use simulation program usually. And a common thing when dealing with these columns called flooding. So I'm not sure if you're going to deal with flooding in mass transfer, but flooding is the idea when your gas velocity is not high enough to basically push through the liquid. So the liquid just overflows your entire column and floods your column, and your column is basically not doing anything. It's not efficient. And there are methods to calculate the flow rate or the point of flooding. And ideally, you want to design your diameter to avoid, or the column diameter to minimize flooding. So usually when designing these columns, you set your diameter by operating 80% of the flooding limit. And as you progress through your career or by experience, you're gonna get a better understanding of what this means. And again, I highly recommend, if you're interested in distillation, to read the chapter in Perry's handbook. They have a lot of information about vendors, about commercial packings, about some specifics of the internals, which are very interesting. Aspen has a tool for just the design of packed and distillation columns called Aspen Icarus. Most of it has been integrated into Aspen Plus. However, you can always find these standalone tools. Okay, so let's just recap. So again, separation specifications, we said previously that recovery is how much of a desired component made it to the stream it was supposed to be in, right? So if I have a feed with composition of A and B, the recovery of A will be how much A is in the top divided by how much A is in the feed, right? It's the pay pressure of A multiplied by Y of A divided by the feed of A multiplied by Z of A. And again, here I'm using P, or most of the time it's pressure, but this is actually the mole flow rate, right? So this is your molar flow rate, this is your molar flow rate. Here P refers to product, sorry. So it's basically the molar flow rate from the top stream multiplied by the fraction divided by the flow rate bottom stream divided by the fraction. Again, just be careful that if your feed is a liquid and your top is a gas, you can use the pressure and the vapor pressure idea as well. Just make sure your units match, okay? Purity. So purity is the concentration of desired component in the stream it was supposed to be in. So this is my product. Purity of A is just a composition of A. So ideally, you want to maximize both the recovery and the purity, right? If I have 100% of recovery, so if all of this A in the feed leaves from the top, but the purity is only 70%, then it might not be good enough, right? So just a few things to think about, or a few metrics to keep an eye on. So let's have a look at an example here. So we'll look at the example of butene's recovery. So in this case, I have a mixture of how many things? 1, 2, 3, 4, 5, 6. Propane, butane, butene, trans-butene, cis-butene, N-pentane, all types of junk in the stream. And you want to have a separation process to recover pure propane, N-butane, a mixture of the butenes, and N-pentane, okay? So, I mean, you can't achieve this in one column, right? This is a multi-distillation problem. So usually in the first step you would need to do intuitively is get the boiling points, right? Which species out of these 6 is the easiest to just boil out? So again, first step, always look at your boiling points. Let's have a look at them. So if I look here, I can see, there's a big range. Propane boils at -42, pentane boils at 36. There's a big jump between propane and butane, right? So about 35 degrees. And then all the butenes here seem to fall in one sort of range, 10-degree range, and I have 4 components, and then there's a second jump to M-pentane. Okay, so looking at the boiling point gives me a better idea about the feasibility of this. So if I want to recover propane, I can probably recover propane from the rest easily, right? If I just have a distillation at a temperature somewhere between these two, I should easily get the propane out. Similarly for the pentane, if I have a distillation step somewhere between these two temperatures, I should get the pentane out relatively easily. And then I need to recover what? I need to recover the butane, which is right here in the middle, from the butenes. So this will be a more complex type of separation, right? So here I have a bit more of a detailed decision to make. But again, when you think about it, should I separate the propane out first and deal with these guys, or should I separate the pentane out first and deal with these guys, right? So there are a few decisions to make when sequencing this separation trade, and this we'll cover in the next lecture. So just be aware of these choices. So this is the final design. So I'm just jumping to the final design, and then we're going to justify it. So again, this is the final design for butane recovery, and as you can see how many distillation columns it took to achieve this separation. 1, 2, 3, 4, 5, 6, 7. So sometimes it's a complex process. So I have my feed here, it enters the first step, and I have a 100 tray column, and I'm separating my propane from one butane, right? So again, I'm separating my propane out first, okay? And then in the second step, I'm separating propane and one butene. So if you think about it, so what I did basically is I separated A and B from the rest. So my first separation point was right here. And then my second separation point will be between these two guys, right? First separation, propane and butene. Second separation point, I'm separating the propane and the butene from each other. So I get my propane at the top, clean. I get my butene at the bottom, clean. And so I'm done with these two guys. So on the bottom, I have a bunch of different species here. So the first distillation column, I just get rid of pentane, right? So I get rid of the heaviest species. So again, let's go back to our boiling point table. So my first separation was between B and C, right? And I got a stream with propane and butane. I took these to another distillation column, and I separated these two from each other. So I got my pure propane, and I got my pure butene. And then I have these four in one stream. I took them to a distillation column at the bottom, and I dropped the pentane out. So now I have my pure pentane here, I have my pure propane, and now I have a mixture of butane, transbutene, and cis-butene. So I need to separate these three from each other, and then I'm going to mix my butenes at the end. Okay, so we did this, we did this, we did this guy, and then the top. So we got rid of the pentene, and then we take our N-butane, transbutene, and cis-butene. So butane and the two butenes cannot be separated by ordinary distillation. So for some reason, distillation does not work for these guys. The boiling points are very similar. The species are very similar. I can't just use distillation. So I need to use absorption. So I'm using an extractive agent. So I introduced furfural as a solvent, and the furfural is gonna eat up the butenes and leave the butane to exit as a pure stream. So here I introduced an absorption stripping type of unit using furfural to try and separate. So furfural is going to eat up the butenes, and it's going to let the butane leave. So I have a stream with butane, which is pure. Butane is done. And now my bottom streams, my two butenes, I'm just going to, regenerate them from the furfural. So the furfural is just is a solvent being looping in between these two units, and then I have my butenes here, and I get my two butenes from the bottom, so I'm able to separate them. So now I'm going to mix my two butenes with one butene to meet the design spec, and then I have my three pure products: propane, pentane, and butane. Okay, so this is the type of decisions you need to get comfortable with when talking about distillation columns. We're going to cover this next week in details, but just try to prepare yourself for this type of thing. Okay. So let's move on to a few points before we end this lecture. So separation is energy intensive. You need to know this. Unlike spontaneous mixing, separation of a mixture of chemicals requires expenditure of some form of energy, because at the end of the day, it's a thermodynamically driven process. Again, separation of feed mixtures, you need to force the species into different locations, right? So I need to have stream A in one place, stream B in another place. And this is done by one of 4 methods, right? First method, creation of heat transfer, shaft work, pressure reduction, whatever. It's called an energy separating agent. Second thing is introducing a solvent. So for example, in absorption, I have a solvent, usually called a mass separating agent. You could have a solid phase, you could have adsorption, similar to the water filters. If you ever bought these water filters and you have this black carbon coming out, so this black carbon just absorbs one of the components or the impurities, and adsorption, basically the molecule sticks to the surface of the solid. And finally, you could have a membrane to achieve this for you. And these are the common separation methods. Read the slide, get comfortable with it, use Wikipedia to find out. If you're not sure about what it means, you want to have a look at what one of these units look like, use Google to find out. Flash columns, distillation columns, absorption, stripping, extractive distillation, azeotropic distillation, liquid extraction, crystallization, gas absorption, liquid absorption, adsorption membranes, all types of things, supercritical extraction, leaching, drying, many different ways to achieve this. And again, as we talked about in kinetics, the logic when doing anything in chemical engineering is, if you build your mass balance, you build your energy balance, you build your continuity equation, you can design anything you want, right? So even though they're all different approaches, if you use your fundamentals, or if you keep your fundamentals in mind when reading the equations governing these units, it becomes clear how you got to these equations, or the driving force, or whatever it is. Okay, so let's take a closer look at some of them. So for vapor separations, the 3 methods which are widely used are membrane. So again, membrane is based on differences in relative permeability of gases, or in a simpler way, based on differences in the size of the molecules. So if I want to separate hydrogen or methane from CO2, hydrogen molecule is a small, cute molecule, 2 hydrogens. CO2 is a large, bulky thing of big carbon, 2 huge oxygens, right? So I could have a membrane, just push the hydrogen out and keep the CO2 on one side. Okay, so this is membrane separation. Absorption, as we said earlier, use a liquid solvent which has a high affinity to one of the components, and this liquid solvent just eats up one of the components and leaves the other component to escape, and then I separate the solvent from the component just absorbed and recycle the solvent back. And they usually have an absorption stripping system unit working together. Third type, which is commonly used for adsorption, is for vapor separation, is adsorption. And adsorption, basically, I have a sorbent, which is a solid type of, let's call it species or reagent, whatever it is. And this solid has a high affinity to one of the molecules. So, the molecule, when I push a gas mixture through this packed bed, for example, if I want to separate hydrogen will stick to the surface of this sorbent or the solid. So usually an adsorption column works because it's a solid, I can't have a stripping column, right? The liquid just flows. Adsorption column, I just have a solid packed with, I have a column packed with my adsorbent solid. I introduce my mixture, for example, hydrogen and CH4. They pass, or hydrogen and CO2, for example, they pass through. The CO2 leaves from the bottom, and I have hydrogen adsorbed to the solid. So now what I do is I have a regeneration step where I switch on a sudden change in temperature or a sudden change in pressure, and then this adsorbent will release the hydrogen and I get my hydrogen out. Okay, so this is the idea of an adsorption. And again, you use adsorption when you have very low concentrations because it's more effective or makes sense economically at lower concentrations. Okay, let's start talking about vapor liquid separations. First one is a flash tank. So flash tank, basically I'm just playing around with my thermodynamics. So if at one temperature, both components exist at the liquid phase, but at another temperature, only one component exists at the liquid phase. So I just induce the shift, thermodynamic shift, and one of the liquids will drop, the other one will stay in the gas phase. Evaporation, you know, it's obvious, you know, you just increase the temperature to get one of these components out. So if I have a mixture of water with some methane in it or something, if I start boiling the water, the methane will start bubbling out and evaporate. And whereas a flash tank is similar to, you know, opening a Coke can or a soda can, because the soda can is pressurized, once I open it, I suddenly reduce the pressure, so the gas or the CO2 bubbles out, right? So I'm just inducing a change in PT conditions to change the thermodynamic state of this mixture. Distillation, just talked about distillation. Absorption, so you could use absorption and stripping for vapor liquid separations as well. Fractionation is like a distillation, but it's used for primarily in oil refining, and fractionation is just a very complex distillation column with a bunch of smaller distillation columns hanging by its side, right? And it's used for vapor liquid separation as well. Mostly used in oil refining and crude oil treatment and stuff like that. For liquid-liquid separation, you have decanting, you have mixer settlers, you have extraction, you have membranes, and these are the most commonly used methods for liquid-liquid separation. Okay. So when developing a separation process, you need to select your method, your energy agent, or your mass transfer agent. So if I'm using an energy agent, I need to know exactly how much energy I need. If I'm using a mass agent, I need to know how will this agent behave? What's the solubility? What's this? What's that? All of these details. Your equipment, your optimal sequencing, and then optimal operating conditions and temperatures. Temperatures and pressures, or operating conditions, basically. And selection of the separation method depends on the feed condition, as we said in the previous slide. So if you have vapor, you need to select the right technology. If you have liquid, you need to select the right technology. If you have a solid, you need to select the right technology as well. Okay, another very important factor in separation, and you're going to talk about this extensively in mass transfer, it's called the separation factor. And the separation factor defines the degree of separation available between two key components of the feed. So for example, if I have component A, component B, or component 1 and component 2, so for separation of component 1 from component 2 between phases I and double I, for a single stage of contacting, the way to calculate your separation factor is using this equation, right? So it's the composition of component 1 in phase 1 divided by the composition of component 2 in phase 1 over composition of component 1 in phase 2 divided by the composition of component 2 in phase 2 as well, right? And SF is governed by thermodynamics, of course, thermodynamic equilibrium. And in the case of distillation, you're going to cover this. I'm not sure if you have seen it yet, but you will see it. You can calculate your separation factor by just dividing your mole fractions, right? K1, K2, you get your alpha. It's called your relative volatility, whatever it is. So just know how to calculate this. And once you get to it in your mass transfer, just be aware of how to calculate this. And these are just more equations, all the stuff for your reference, etc. Okay. Let's move on to this is the last slide here. So impact of separation specifications. This is something you have to be aware of when doing your projects, is your cost will start to significantly increase as you enhance your purity, right? And you need to stop at a point. You need to find out your minimum acceptable purity or impurity, for example, for product, to avoid having a distillation column which is $300 million when doing your design projects, okay? So I can get between 90 and 99%. The cost increase is not that much. If I want to get from 99 to 99.9, might be acceptable. If I want to get to 100%, cost becomes infinite. Cost starts, diverging almost infinitely, right? So just keep this in mind. So when doing your separation and you find that your distillation column is extremely expensive, maybe try to reduce your purity spec a bit, see if it makes more sense, and you start having a decision trade-off. All right, so this is the end of this lecture. So you should be familiar with the industrial separation methods, the basis of separation, and you should understand the concept of separation factor and try to link it with what you're covering in mass transfer as well. All right, so thank you very much. Please be aware of the deadlines mentioned at the start of this lecture, and please come to office hours if you have any questions.